Welcome to Chapter 2, The Way Earth Works, Plate Tectonics, from Marshak's Essentials of Geology, 7th edition. Let's get started. This slide gives you links to the various sections in the textbook. It might be helpful you to have either the hard copy or the book online in case you need more detail on a particular topic. So how do we know why the Earth looks the way it does? Well, much of the credit can go to a German meteorologist named Alfred Wegener. For pretty much ever, humans thought that the Earth's surface had always looked the same. But in 1914, Wegener published a book called The Origins of the Continents and the Oceans. He hypothesized that at one point in the past, all of the continents were together. He named that supercontinent Pangaea, and these ideas came to be known as continental drift. Here's our boy Alfred Wegener. You can see that in the past, he had this idea that everything was together, and over time, the continents drifted apart. But scientists always want to know why things happen. It's not enough to make a claim. You need to supply evidence and explain the reasoning as to why that evidence supports your claim. Without the why, you really don't have a strong enough argument. So sadly, Alfred Wegener died in 1930 while on expedition in Antarctica without ever figuring out that why. He died thinking that his ideas were not very widely accepted. However, some other scientists appeared on the scene in the 1960s. A guy named Harry Hess, who was an American geologist, proposed that as continents drift apart, new ocean floor forms between the separating pieces. Then Robert Dietz, an American marine geologist, came in with the catchy title of seafloor spreading. So they proposed that when the continents move together, old ocean floor bends down and sinks into the Earth's interior. Now this is known as subduction. From what we can tell, the Earth's lithosphere, the outer, relatively rigid shell, is made of about 20 plates that slowly move relative to each other. We have many observations to confirm these ideas, enough that we can call this a theory. So plate tectonic theory uses the Greek root tekton, which means builder, because as the plates move, they build geologic features. This can be considered a grand unifying theory because it successfully explains many geologic phenomena that we see out in the world today. So what is the evidence that helped Alfred Wegener come up with this idea of continental drift? Well, the most obvious evidence is the shape of the puzzle pieces, the continents themselves. As you can see, they fit together kind of like a jigsaw. Africa and South America fit very closely together. Australia, Antarctica, India, and Africa, they all kind of tuck into each other as well. We even see Greenland, Europe, Asia, and North America that can kind of match up. This is a very compelling clue to this idea that the continents used to be joined. Then we have these things called glacial striations. Well, glaciers are rivers or sheets of ice that flow across the land's surface. As they move, they scrape up bits and pieces of rock and carry that debris along. The bottom of the glacier, with these sharp grains, scratch the surface and leave marks called striations. As the glacier melts, all of that junk that it collected along the way falls and forms deposits of till, which may cover and bury those striations. So Wegener knew that there was an ice age in the late Paleozoic era, about 280 to 260 million years ago, and he saw evidence of glacial striations in South America, Africa, Australia. But these aren't polar regions, so how could there have been glaciers in areas that are not really that cold? So let me show you some pictures. Here's striations that show up on the south coast of Australia from the late Paleozoic age. If you look at the current position of the continents, the marks don't really make sense. South America is very separate from Africa, which is very separate from Australia. But if you look at Pangaea joined together, you can see that a polar ice cap might explain these striations. Wegener reasoned that the continents had been joined together at one point, and then these striations made more sense. Like that. So then we have climate belts. As we look at rocks, we can find evidence of past climates. For example, in tropical regions that are covered in swamps and jungles, thick layers of plant materials build up over time, and when they're buried, they turn into coal. Reefs develop in clear, warm waters of shallow tropical seas, and the existence of coral and reefs indicate tropical climates. If you move to subtropical regions, which are on either side of the tropics at the equator, you find deserts, where sand dunes form and seawater evaporates, leaving salt behind. Wegener then proposed that the distribution of coal, reefs, sand dunes, and salt deposits could define Pangaea's climate belts. So you put the continents back together into Pangaea, and you can see that coal and reefs are found along the southern coasts of North America and Europe and the northern edge of South America. Desert sand and salt flats are scattered as you move away from the equatorial lands into subtropical regions. If you look at a modern map, the rock layers are scattered around the globes at different latitudes. But during the late Paleozoic, these bands line up perfectly if Pangaea was all one big piece. Kind of cool. So this is my favorite piece of evidence. These are the fossils. Wegener found varying fossils of some animals and plants around the globe. So he looked particularly at Mesosaurus, Cygnognathus, I think I'm saying that right, and Lystrosaurus, all of whom lived on land. None of these little animals could swim across oceans. He also saw Glossopteris, which is a fern, and ferns don't swim either. So he found these on southern continents. He theorized that animals and plants evolved independently from each other, so these fossils could have only migrated to different locations if they were all on one big piece of land. Kind of cool. Now we look at the what are called matching geologic units. You look at the matching rock types that are pictured in purple and in brown on this map. It would be really hard to explain these if you look at modern day topography. How could the very same Prototerozoic mountain belts and Archean crust form if they had been separated by an ocean? You take the ocean away and move those puzzle pieces together, and all of a sudden, it makes sense. Wegener also noticed some distinct rock assemblages, or these matching geologic units. The same types of Precambrian rocks show up on the east coast of South America and the west coast of Africa. The Appalachians in the US and Canada look very similar to the mountains in southern Greenland, Great Britain, Scandinavia, and northwest Africa, all of which would have been connected during the time of Pangaea. So not only do the shapes of the modern day continents fit together, but the rocks themselves near the coastlines also match. So there was some criticism, right? So in spite of really good evidence, right, remember, we have puzzle pieces, we have glacial striations, we have climate belts, fossils, and these matching rock assemblages, right? Even in spite of all of that, we still don't know the why. This picture is the last known image of Wegener. He died while on an expedition to Antarctica. He was actually going down there to visit some other meteorologists. So he died not understanding the why, but he set the stage for a very, very strong evidence for plate tectonics, what we know today. So around World War II, right, we developed sound navigating and ranging, or sonar, right? This was developed so that because there were increased use of submarines. Scientists needed to know the depth of different parts of the ocean, and just like a bat, sonar uses sound waves bounced off the sea floor to determine depth. This is called bathymetry. Bathy meaning deep, meter meaning measurement. So if you look at a bathymetric map of the seafloor, you can see a lot of the features that we know today, like mid-ocean ridges, deep ocean trenches, fracture zones, seamount chains. We can do the same thing today using satellite data. So these, for example, are bathymetric profiles or cross-sections of the Atlantic at the top and the Pacific down at the bottom. And you can see distinct features. You see abyssal plains, which are broad, relatively flat regions. They're like 4 or 5 kilometers below sea level. You can see mid-ocean ridges. You can see submarine mountain ranges even. Deep sea trenches are bordering volcanic arcs, and you see curved change volcanoes. You see fracture zones. They're at right angles to mid-ocean ridges. And seamount change, like the Hawaiian Islands, which may or may not be active volcanoes. You can also see isolated seamounts or underwater dormant volcanoes. There's some more on page 51 in the textbook if you want to see images of some of these features. So as you look at this section of the seafloor, find the mid-ocean ridge, or the MOR. The sediment made of clay and tiny shells covers much of the ocean floor. The farther you get from the mid-ocean ridge, the deeper the layer of sediment becomes. But it's too thin to have been present for the entirety of Earth's history. Based on some observations, scientists have found that the composition of oceanic crust is fundamentally different than continental crust. The crust under the oceans is primarily made of basalt, and basalt, it's basically one kind of rock. There is a great variety of rocks on continents. So the older, thicker sediment is located farther away from the mid-ocean ridge, where new ocean floor is being built. What do you notice about this map? What do those red dots mean? Well, they're earthquakes, right? So after World War II and the better and when we had better maps of the world's oceans, it became clear that volcanoes are not randomly occurring. That earthquakes are not randomly occurring. They actually define parts of the Earth which are moving relative to each other, right? So you can see those red dots representing the volcanoes show you the outlines of mid-ocean ridges and transform faults and deep-sea trenches, like you would see along the edge of Japan or South America, right? So this gives very good definition to these plates that we know about. Now, after World War II, there were two researchers at Columbia University, Marie Tharp and Bruce Heezen, who noticed that the mid-Atlantic ridge had a narrow valley along the entire length of the ridge axis. It looks like a scar running down the center of the Atlantic Ocean. The topography of this valley resembled that of the East African ridge. So Harry Hess of Princeton realized that this thin sedimentary layer of the ocean floor might be younger than the continents. But how does this happen? Well, he suggested that maybe the magma rises up at these mid-ocean ridges, it solidifies into basalt of the oceanic crust, and then widens the basin of the ocean. With this idea of seafloor spreading, there might be other places where the seafloor sinks back into the mantle. Maybe the earthquakes have something to do with it. So as we've seen earlier, we know that the Earth is like a big magnet, right? There's a North Pole and a South Pole. And there's this shield-like magnetic field around the planet with these very distinct magnetic field lines, right? So the Earth's magnetic field is caused by this molten iron alloy at the outer core. But if you look even closer, the magnetic and geographic poles don't match. They're very close, but they're not the same. Okay, so there's about a 10-degree separation between between the axis of rotation and the magnetic axis of the Earth. So we look at what's called declination and inclination. A compass doesn't really point to true or geographic north, okay, but it points to magnetic north. Now, both magnetic north and geographic north are high latitudes, very far away from the equator. The angle between the direction in which the compass needle points and a line of longitude at a given location is called magnetic declination. So declination depends on where you are on the Earth. Now, if you look at this picture of the poles, the red line on the map shows the North Pole's changing location after the past 2,000 or so years. Again, very well north of the equator, but certainly not in the same place. I'm trying to go forward here. Here we go. Okay, so now we have magnetic inclination. Now remember those curved field lines, right? The compass needle will tilt towards or away from the Earth's surface depending on its proximity to the poles. And this changes with latitude. That difference in the tilt is called inclination. So if you look at the red end of the magnet, it always points directly towards the Earth at magnetic north. If you look at the magnet well south of the equator, the one at the bottom of the picture, its red end is tilted away from the Earth, while the white end is tilted towards magnetic south. That angle, that tilt, is called inclination. So what's really weird is Earth's magnetic field actually kind of wobbles. So if you look at rock samples like this cute little geologist is doing right there, kind of looks like me with the curly hair. But if you look at this geologist, we can determine where Earth's magnetic poles were when rock is actually formed. So look at that red and white magnet in the rock sample. That represents what's called a paleomagnetic dipole, literally an ancient magnet with a north pole and a south pole, right? So remember that Earth's outer core is melted iron alloy, and it's a conductor of electric current. More or less, Earth's magnetic poles lie near the geographic poles. So we can use this magnetic inclination and declination for any rock sample, and we can figure out where and when that rock was formed, and also where magnetic north was. Because magnetism is preserved by rocks, right? So iron minerals and rocks archive the magnetic field at the time of formation. In hot melt or hot magma, magnetic dipoles are just randomly oriented. There is no permanent magnification. As the temperature decreases in that lower part of the image, the magma cools. The magnetic dipoles in iron-bearing minerals become aligned. They line up like little shoulders, right? So the magnetic signature now is frozen in the rock, and we can tell where the poles were when that rock was formed. Kind of cool. I keep saying that, but it is. So now we have this idea of a paleo pole. Paleo means ancient, remember. So why is it that paleomagnetic dipoles in ancient rocks point, or why don't they point to where today's magnetic field is? Well, look at this sample on the side here, right? Inclination and declination changes in layered successive rocks from lava flows. So scientists want to know why these paleomagnetic dipoles in ancient rocks don't point to where today's magnetic field is. They came up with this idea of a paleopole where the magnetic dipoles were in the past. Further investigation leads to what is called the apparent polar wander path. So again, this is apparent. This is not set in stone. This is not true fact yet, but we have very good evidence for this, right? So, okay. So take a look at the apparent polar wander path for North America in red and Europe in yellow, up at the top of that globe at the top. If the magnetic pole moved while the continent stayed in place, as in figure A, all of the data should give you identical paths. Well, the red line and the yellow line are clearly not identical. However, if you assume that the continents move relative to a fixed pole, then you see those paths, those apparent polar wander paths, and they make much more sense. Now, throughout human history, the north end of compass needles have always pointed to the North Pole, or have they? Right? We've discovered over time that there are periods of reversal where dipoles will point in the opposite direction. So again, we have this magnet-like attraction, or that magnet-like behavior of the Earth. So we've concluded that every so often the dipoles flip, and it does so pretty quickly. So we consider normal polarity to be the same orientation as we have today, and reverse polarity to be the opposite, when your magnetic north will point to the South Pole. It's kind of weird. But we have evidence of this that's recorded in iron-rich rocks, like basalt that's at the bottom of most oceans. So you'll see that magnetic reversal down below where it's opposite of what we have today. So this image over here that my head is on top of is a chronology of magnetic reversals, right? So you look at the age of rocks like basalt. This image is giving you about a 4.5 million year timeline, and the larger sections with the dotted lines are called crons. Those are long intervals of a given polarity, whether it's normal or reversed. Within that, however, you can see little anomalies. Those are called subcrons. They are short intervals of opposite polarity within a larger cron. Okay, so the longer time spans, the crons, are named for famous researchers like Gilbert or Matayama. Subcrons, these little shorter intervals within a longer cron, are named after localities like Nunavak or Jaramillo. Those dark gray periods are normal polarity. The lighter brown is the reverse polarity, opposite of what we have today. So thank you, Shakira, because rocks are like hips, and they don't lie. Okay, so I cracked myself up. So check out these magnetic reversals in lava flows, right? You can see this image of an erupting volcano and the striping of the rocks underneath it from successive lava flows. Well, as you go down deeper into the earth, you can see that the magnets have reversed over time and switched back and forth. And because that lava cools and freezes those molecules in place, we have this magnetic record. Looking at the ocean floor, you see the same thing. So we see magnetic anomalies. When you use magnetometers, things that measure magnetic field, and they're dragged along by ships that move perpendicular to mid-ocean ridges, and they can record alternating strong and weak magnetic fields. When scientists did this, they didn't see uniform field strength. A magnetic anomaly is the difference between the expected and the observed strength of Earth's magnetic field. Positive, strong magnetic anomalies and negative or weak anomalies line up to form these stripes on the ocean floor. The stripes are symmetric around basaltic mid-ocean ridges and are very different than what we see in rocks on continents. Off the west coast of North America, for example, the map of positive and negative anomalies look like the stripes on a zebra. Like that. This is off the edge of North America heading up towards Alaska. So we do see this beautiful symmetry in seafloor spreading. So what it predicts is that magnetic anomalies should be mirror images across mid-ocean ridges. So if you look at this, that inset, the ridge axis is marked in red in the middle, and on either side of this, they're very, very close because that's what they're supposed to do. The new rock is being formed at the center, and as over time, they move apart from each other. So why do we have these stripe patterns? Well, we have positive anomalies when the seafloor rock has the same polarity as today's magnetic field. Negative anomalies form when polarities are reversed. So take a look at these arrows, right? So in physics, the big arrow always wins, right? And bigger forces are represented by larger arrows. Well, magnetometers can detect and record strong and weak signals from the ocean floor and plot them on a map. So seafloor spreading takes place at a fairly constant rate, so we know that the width of the stripes corresponds to how long those polarity intervals last. My head is in the way, but over on the left, the positive anomaly shows a large force. A negative anomaly, which is behind my head but smaller, indicates a smaller force, a weaker force. So notice the patterns if you look at the mid-ocean ridge, right? The vertical red stripe down the center is the mid-ocean ridge. And the width of the magnetic stripes in seafloor basalt is proportional to the duration of the normal or reverse magnetic field conditions. In other words, the wider the stripe, the longer the period of that magnetic field polarity. So, plate tectonics. The lithosphere is made up of the crust and upper mantle. It's thicker under the continents and thinner under the oceans. The asthenosphere is pictured in orange, and it's underneath this lithosphere, the crust and upper mantle, and it's soft and gooey, kind of like chewed up gum, and it's able to flow slowly, but flowable nonetheless. So as you look at the lithosphere and asthenosphere, they're fairly rigid, right? They're fairly stiff, but they will bend under heavy loads. Think of something like a glacier or a volcano. You can see over on the right that if there is a heavy load on the surface of the planet, it can actually bend and crack the lithosphere, and the asthenosphere flows away from that pressure. So here are these plates. We have these big, huge plates that are kind of boogie boarding on top of the asthenosphere. And if we use a model of a piece of wood and cork floating on water, it gives you some insight. It's not ideal because water is more dense than the oak wood, but the asthenosphere and the lithosphere mantle have a range of density values, and sometimes there's a little bit of an overlap. So now we're on to plates, right? We have these big, huge, massive chunks of earth, and some plates are oceanic, but others have both oceanic and continental. If you look at a map of these major plates, you can see active continental margins along the edges of plate boundaries. Passive margins are not on plate boundaries. For example, find the western edge of North America. That is also the boundary between the North American and Pacific plates. That is an active margin. The continental shelf along the eastern edge of North America, that's called a passive margin. It's this relatively shallow part of the Earth that is not active. So the yellow arrow is an active boundary, and the red is a passive boundary. So here are all these pieces of the puzzle exploded. So you can see the variety of shapes and sizes of tectonic plates is crazy. The only thing I would caution is that this image takes a three-dimensional object and fits it on a two-dimensional flat piece. So the Antarctic plate is large, but not that large. Okay, so just keep that in mind. We're going to look at map projections later on in the course. So the location of earthquakes, we've found, really help us define plates. The location is not random. Look at all those red dots, right? The distribution of earthquakes defines plate boundaries. Notice there are very few earthquakes that occur in the more stable interiors of the plates. There are some, but they're much less common. There are three types of plate boundaries. We have convergent plates, which come together, divergent plates, which are moving apart, and transform plates, transform boundaries or transform faults, where two plates slide by each other. So let's take a look at each one. Okay, here is divergent boundaries, and this includes seafloor spreading. So this is when two plates are moving away from each other. Seafloor spreading produces new seafloor at mid-ocean ridges. As seafloor spreading progresses, the ocean basin widens and these continents move apart. So you can see in the top image that mid-ocean ridge is very well defined, and there's a small bit of ocean on either side. However, as the plates spread apart, you get a larger and larger ocean basin. So a mid-ocean ridge, an MOR, right? Speaking of mid-ocean ridges, they're much shallower than the deeper abyssal plains. The ridge is offset along its length by these transform fault fracture zones. They are perpendicular or 90-degree angles to this mid-ocean ridge. The mid-ocean ridge is pictured as a red stripe going down the center of the Atlantic Ocean, and once you see it, you will never unsee it. It is a very obvious scar on the surface of our planet. So looking at a cross-section of a mid-ocean ridge, you can see that there's this big magma chamber underneath the ridge axis. The molten rock produces what is called pillow basalt. There's actually a really good picture of this in the textbook. Basalt is what oceanic crust is made out of. So there are basalt dikes which are perpendicular to the sea floor, and they push upward to the left and the right of the upper level of this diagram. Gabbro, which is a denser rock, forms deeper down below. Seawater that has seeped into the crust is heated by the magma, and the dark-colored minerals that are dissolved in this water accumulate and create like a chimney-like structure, and hot mineralized water spews out of these vents. They're known as black smokers. Things like bacteria and shrimp and worms live there. It's like having a hot tub down deep in the ocean. So when we form new lithosphere, okay, the further away we get from the mid-ocean ridge, the thicker the lithosphere gets. Remember, the lithosphere is the crust in the upper mantle. So as the plate moves away from the ridge, it cools, causing these molten parts of underlying asthenosphere to crystallize and to solidify. The process continues for millions and millions of years, causing the lithosphere to thicken downwards and become thicker and denser with age. The section B of this image shows that as you are farther away from the mid-ocean ridge, the crust, the lithosphere, is much, much thicker. As we get away from the mid-ocean ridge, the rocks get older and older. So new crust is being made at the MORs, right? It makes sense that this is where the youngest oceanic floor is. The oldest part of the oceanic floor is farther away from the axis because those plates are moving farther and farther away. So on this map, the red is the younger part of the scale. Over to the blue-purple side, that is the very oldest part of the crust, at least the oceanic crust. So now we have another type of boundary. These are convergent. This is where boundaries are coming together, and this is where subduction happens. Remember, sub means under. So this is when two plates move together, and subduction happens when one plate sinks below the other. So the downgoing plate sinks beneath the overriding plate in this process called subduction. Trenches occur here, and one of the most noticeable trenches, actually there are two of them. One, like where the Pacific plate subducts under Japan, you have a very deep trench. And on the coast of North America, there's a very, very deep trench on the western edge of the North American plate. These are very common. Trenches are very common at convergent boundaries. So you can see here, this is the edge of the Pacific and Japan. And you can see that deep trench that's, again, sort of like a scar that runs down the edge of the plate. So looking a little bit more like subduction, okay, subduction is like an anchor sinking. When you put the anchor out, it slowly starts to sink. So over time, it gets deeper and deeper. The water actually gets pushed out of the way by this sinking anchor. As the lithosphere sinks, the asthenosphere flows out of the way, but it moves much more slowly. And there are a lot of earthquakes that happen along these convergent boundaries, up to a depth of about 660 kilometers. This zone where the earthquake occurs along a subduction zone is called the Wadidi-Benioff zone, and it's named after the two people who discovered this idea. Kind of cool. I'd love to have something named after me in science, but not something gross, something nice. So what else can we have happen at convergent boundaries? We know that we get subduction. Well, subduction can, along the edges of continent, can produce volcanic arcs like the Andes in South America, where subduction between oceanic lithosphere produce, there are other areas where you can get island arcs like the Hawaiian Islands. Those are formed when oceanic when you have subduction beneath oceanic lithosphere. So you should go look those up on the map. They're actually really kind of cool. Okay, the third type of plate is called the third type of boundary is called a transform boundary or transform fault. This is where plates slide past each other, and this happens with no change in elevation, right? You don't have any new plate being formed. You don't have any old plate being consumed by the earth or being subducted back into the earth. They just slide past each other. So transform boundaries often happen on oceanic crust, but they can also happen on continental crust. So on this map, you can see the mid-ocean ridge in red up on the top picture over at the left, and the fracture zone is in yellow. Fracture zones are not active. There are no earthquakes along these zones. The fracture zones are perpendicular to the mid-ocean ridge. If this gets confusing, ask me about it in class. So active transform boundaries. These transform boundaries or faults on the ocean floor connect and offset ridge segments. Active faulting is indicated by earthquakes only occurs in the part of the fracture zone between the ridge axis. So along the red line, that's where the active faulting is occurring. The yellow dotted lines, there's no faulting going on there anymore. So this is where you can actually see transform boundaries on continental crust. For example, the San Andreas Fault in California, this is where the Pacific Plate moves northwest relative to the North American Plate. You can see it both in an aerial image and on the map that's drawn on the right. Okay, so now we have special locations as well, because there are weird things that go on in certain areas. You have something called a triple junction. That's where three plates intersect. So a good example is where the Southwest Indian Ocean Ridge intersects two arms of the Mid-Indian Ocean Ridge. This is called a ridge-ridge triple junction. You can see a transform junction if you look just north of San Francisco on the previous slide. Hotspots. Hotspots are, or hotspot volcanoes, are probably a consequence of mantle plumes where the energy is moving upwards through the mantle. So as the plate drifts over a hotspot, a chain of extinct volcanoes, it's called a hotspot track, forms. The Hawaiian Islands are an example of a hotspot track. The islands increase in age as you move away from the present hotspot. The orange arrow shows the direction of the plate movement. An animation is included at the end of the slide that might help explain a little bit better. Okay, hotspot tracks. So geologists do recognize that there are numerous hotspot tracks around the world, and the tracks provide clues to both the direction and rate of plate movement. The dots on the map, like on the continent, look on Africa, there are dots on Africa. They represent the locations of selected hotspot volcanoes. The red lines represent hotspot tracks. The most recent volcano is at one end of the track. So some of these volcanoes are extinct. Some hotspots are fairly recent and don't have tracks. These dash tracks were broken by seafloor spreading. So all of these different phenomena are happening at the same time and causing some really incredible features to be formed on the surface of the Earth. So how do plate boundaries form? How do they die? Well, continental lithosphere stretches out and thins, and the upper crust breaks by faulting. The upwelling asthenosphere initiates or starts volcanism, which is active volcanoes. Rifting may even split a continent in two. Again, there's an animation at the end of the show that might help explain a little bit better. So the East African Rift is a good example of an active rift. The Red Sea, which is marked by the red arrow on the map, started as a rift but evolved into a relatively narrow ocean basin. The rift axis becomes a mid-ocean ridge, and these faults result from stretching and thinning continental lithosphere. The aerial picture shows the northern edge of the East African Rift, showing faults and volcanoes in the area. Again, incredibly fascinating to see the model, the cartoony-like drawing, and then the actual thing on the surface of the planet. You can have continental collisions, and this is pretty much just what it sounds like, where you have this continental collision starts after subduction has consumed oceanic plate that was once in between two continents. Continental crust is too buoyant or floaty to subduct. So when two continents converge, the rock undergoes compression and shearing, and a mountain range develops. There's a video at the end of the slideshow showing you this as well. Best place to find this on the surface of the planet is where the Indian plate is bashing into the Asian plate, Eurasian plate, and it's forming the Himalayas. Like this. Pretty incredible. I'm going to show you a video on the formation of Everest that I think you'll like. So moving plates, right? What drives plate motion? Well, it's much more complicated than simple convection, which is pictured on the right. That's like watching water boiling in a pot on the stove. It's a relatively simple process, but it can't explain, simple convection cannot explain all of the different types of plate movement that we see. So we've come up with a more modern version that has warmer and cooler areas. It's indicated by the different colors on the map on the right. Convection cells are no longer thought to drive the motion alone. Now we include convection and two forces, one called ridge push force and the other called slab pull force. Remember, in physics, there's only pushes and pulls, and physics are a big driver of the movement of these continents. Okay, so ridge push develops because of the gravitational energy associated with the elevation of the mid-ocean ridge. Simply put, the lithosphere of the mid-ocean ridges are at a higher elevation than the adjacent abyssal plains, those lower flat areas that are deeper in the ocean. So as that ridge develops, it pushes to either side. Slab pull develops because old oceanic lithosphere is more dense than the underlying asthenosphere, so it sinks down below. All of these forces are really shaping the surface of the planet. Now, how do we know how fast things are going? Well, the velocity of plate motion can be described in two ways. Relative plate velocity describes how one plate moves compared to another. Absolute plate velocity describes motion compared to a fixed reference point below the plate. Geoscientists measure the distance between the ridge axis and a location of the ocean floor at a specific edge. They do some fancy math here, like velocity equals distance divided by time, and they can figure out the speed and direction of plate movement. When you put all of this together, you can see just how diverse the plate tectonic interactions are on Earth. Remember, you have divergent boundaries, convergent boundaries, transform boundaries. You have mantle plume hotspots that are not tied to any sort of plate motion. The diversity is absolutely incredible. And as the course progresses, we are going to investigate a lot of these different features. Over time, as a result of plate tectonics, this map is constantly changing. Our map of Earth is constantly changing at a very slow rate, but continuously. Here is the assembly and eventual breakup of Pangaea during the past 400 million years or so. From here on out, the rest of the slideshow gives you things to think about, some narrated videos and animations that I think might help explain some of these very complicated concepts, and there are also some resources you can find online. As always, if you need anything, please feel free to speak up in class.